Okay, this is going to be the last section we do in this chapter. So we'll be having a chapter test after this. Even though there are more sections, we're not doing them. So this is 8-6, day 1 of 3 days. Okay, we're going to have another technique for finding the volume of the region after rotating. So a little introduction first, a new formula, and then we'll get to a couple of examples. So let's say we had this parabola. And we're going to stop it right there. And we're going to take the region from 0 to this point, A. Chop that off. And we're going to revolve this around the y-axis. Well, so far, we've always drawn our rectangles perpendicular to the axis we're going around. So in this case, I'd be drawing the rectangle this way. And because of the gap here, this would create a nice washer. And I don't have an issue until I get up to this top part here, where when I draw in the rectangle, I'm making the function touch itself on the right and the left. And we can't do that. There's no touching, making the function touch itself here. So it's impossible to draw a rectangle in this horizontal position. So what we're going to have to do is draw the rectangles parallel to the axis that we're going around, and we're going to create a new shape. So start it over. Now if I draw my rectangles parallel to the y-axis, and I revolve around all the way through here, my rectangle is going to touch the function and then the x-axis all the way through. So I'm consistent. That's what has to happen. Function, y-axis, top minus bottom. Okay, what these shapes create as they rotate around are called shells, cylindrical shells. And I'll show you them in the book. I'm not going to try and draw them again. The drawings are terrible. So, 1 second. Right here. So here was the shape I had. And here's the shell that's coming around. It's the cylinder shell here. You get this. So when I take that vertical rectangle and I rotate around, I create another cylinder, but it's a cylindrical shell, they call it. And then over here, they just show you, as you come in, the cylindrical shells just fill each other in all the way to the axis there. So let's look at a cylindrical shell and see if we can come up with the formula for it. So think about a sheet of paper rolled up that has some thickness to it. So the shells would look like this. There's some thickness in here. Okay, so when we cut a cylinder open, though, we get this rectangle shape. And it's a very thin, actually rectangular prism. And we want a formula for the volume of this rectangular prism that we would rotate around and make this cylindrical, like they're calling a cylindrical shell. So, for the volume of this, we need length times width times height. Length, width, and height. Well, the length, if you think about it when it's curled up, that's the circumference of this cylinder. So the length is our circumference of a circle formula, and the circumference of a circle is pi times the diameter, or 2 pi r. So I'll go length, width, and height. Length is 2 pi r. Width is staying width, and height is staying height. So in our picture, what's happening, I'll point out each one. So I forgot my integral here. Integral from A to B. So the radius, if you think about it, because I'm going around the y-axis, the radius is the distance from the axis over to each rectangle. So in this case, I'll write that down. Distance from axis to each rectangle. So in this case, it's a horizontal distance. And what we call horizontal distances in the coordinate plane is an x value. It's over x units, and it just keeps changing as we go all the way through. So the radius is either going to be x if the rectangles are in this vertical position, or there'll be a y if they're horizontal, and we'll get to one of those later. So your radius is always either going to be x or y, unless we're going around a different axis. But for now, we'll just stay right here. The height, normal height, the height of our rectangle. So height of the rectangle. And that's either going to be top minus bottom if they're in the vertical position, or right minus left if they're in the horizontal position. So top minus bottom, or right minus left. And then the other thing you need to know is the width. And the width, again, is just our little change in y or change in x. In this case, dx. If they're laying the other way, it'll be dy. And the 2 pi is a constant that's going to carry along. Okay, once we've got this formula, it's just like we've been doing. So let's try a couple, probably one each way. Sometimes with the shape they give you can be done either with shells or with washers or cylinders, but today we're just going to practice all shells. So our first example, we want the region bounded by y equals 2x minus x squared, the x-axis, and rotated about the y-axis. Okay, graph first. Upside down parabola. Two x minus x squared. Okay, vertex is over. It went through the origin. So bounded by this and the x-axis. So I'm taking this region, and I want to do this with cylindrical shells. Shells is my technique. So to make it shells, I have to draw my rectangles parallel to the axis that I'm going around. So parallel to the axis. With the washers and cylinders, we always do them perpendicular to the axis. So I need to draw parallel to the y-axis because that's what I'm rotating around. I wouldn't be able to draw them perpendicular anyway in this case because I make the parabola touch itself, so it would be impossible to do it the other way. So we're going up and down, going around the y-axis. Right away, this tells me this distance is a dx, I know I want to see all x's in my integral. So I want x boundaries, 0 here. I have to find this one. So I'll do that first. What I know about this point is that the y value is 0. I don't know what the x is, but I know the y is 0. So I can put 0 in for the y and then solve for the x. So if I do that, I'll do it right here. 0 equals 2x minus x squared. This is to find my boundaries. I'll factor out an x. That leaves 2 minus x. Thing 1 times thing 2 equals 0, so x equals 0, which I already had. And then 2 minus x equals 0. X equals 2. So my other boundary is at 2. Okay, so I'm going for the integral now. I know it's going from 0 to 2. And my formula for a cylindrical shell is, I'll write it above here, 2 pi r h w. So my 2 pi carries along. Radius, remember, is that distance from the axis of revolution over to each rectangle. That's a horizontal distance. That's a distance of x. Remember, radius is always either going to be x or y. So r is an x. The height is top minus bottom. Top minus bottom. This is an easy one because there's really only one equation here. The other equation is 0, but just to keep the pattern going. So the top is the function. That's 2x minus x squared. The bottom is the x-axis. That's the line y equals 0. So 0 is my bottom equation. So it's just 2x minus x squared. So in parentheses, my height is 2x minus x squared. And my width is that dx that I already wrote down. That helped me decide what I wanted to see all the way through here with x's. All right. Now the calculus part. I'm going to pull the 2 pi out in front. 0 to 2. I'm going to distribute the x in. That'll give me 2x squared minus x cubed dx. And now I can integrate each term with the power rule because that's the first power. It's like the parentheses are gone. So the 2 pi will get multiplied by both of these. So that's why the parentheses are there. So power rule says add 1 there. Multiply by 1/3. Add 1 there. Multiply by 1/4. Evaluating from 0 to 2. Okay, and then it's just calculating. Y equals. So don't forget the 2 pi. Parenthesis. 2/3 x cubed minus 1/4 x to the 4th. Started at 2. 8.38 minus the 0 is 0. Oh yeah, I could have looked. So 8.38. Or an exact value, 2 cubed is 8. 8 times 2 is 16. 16 times 2 is 32 pi over 3. Just not necessary. Okay, let's try one more. Practicing the shell technique. Let's see. Okay, we've got y. Let's see. The region under y equals x to the 2/3